Dr. Ashish Awasthi from IIT Calicut. So, is he sharing his screen?
Professor Ritesh, if you will share your screen, that will automatically be removed, the layer screen.
Okay, so it won't affect. Okay.
Yes, yes.
Um, so let me share my screen. Maybe that is a good start. Is my screen visible to you?
Yes, yes, Professor Ritesh, it is visible.
Okay then. Just a minute. Just a minute. Yeah. My Adobe Reader is visible to you. That PDF, the PPT is visible.
Yes, yes, PPTs are visible.
Okay. Okay. So uh, yesterday actually I talked about interactive programming and uh, loops and conditional statement in MATLAB, and after that I touched upon the concept of vectors and matrices. In fact, if you have gone through yesterday's slide or if you have attended it, I mentioned that in MATLAB every variable is a matrix. A scalar quantity is 1 cross 1 matrix, and vector quantity is 1 cross n cross 1 matrix, and you have a square matrix n cross n, and you have non-square matrix n cross m. So today actually I have to talk about the ODE and PD problem. Actually, it's a 2 semester course, at least 2 semester course, but I have to cover only in 1 hour. So I'll be just taking two basic examples, one from ODE and one from PD. And I purposefully took the ODE first order ODE example, and I will be talking about the Euler's method, which is discussed by the previous speaker, so that we have already a foundational thing in our hand. And then I will talk about the first order PD, which is like a hyperbolic PD and hyperbolic linear PD basically. And I'll show you how we can find the solution of those problems in MATLAB. So as I mentioned that first is first order initial value problem, and then I'll be talking about the PD, which is a transfer problem. So the previous speaker talked about this kind of first order initial value problem, and derivation was given to all of us at how we can compute the approximate the solution at a later state. So initial state y0 at y at t0 equal to y0. This value y0 or y subscript 0 is known to us. It's the initial state, and we want to find out how the trajectory or how the value of y will evolve, or it is actually throughout the interval how it is varying, and that can be identified by this expression. And here we have h as a step size. So what h is doing here is actually we have the solution at time t equal to t0, and we want to find out solution at some later time state, so say capital T. So h is the number of is the step size. So what we are going to do, we are going to discretize the whole interval from small t naught to capital T, and we will divide it into n parts such that each part is of h size. And it is important to consider the step size, some condition on the step size. Specifically, the choice of step size becomes more important when you are using the Euler explicit method, because it actually, I don't know how to uh, i- is it visible, or this thing is coming? Okay, no. So stability able to Euler method. So when uh, what I was want to emphasize on this slide that if you take a bigger step size h, then your method will be unstable. It will blow up. So, for example, I am considering this initial linear initial value problem y dash equal to minus lambda y, and its exact solution we all know is given by this expression, which is basically exponential of negative lambda t, and it actually this solution show exponential degree, or this kind of equation is also called damped equation or damped solution. And if we use the Euler method recursively, you will get this recurrence relation. And so basically the solution at n plus 1th step is related with the solution at initial solution with some factor, and this is called the magnification factor. So it has to be smaller so that uh, it does not blow up. In what sense it should be smaller? That the modulus value of 1 minus h lambda should be less than 1, and that if you derive this, it provides us the condition that the step size should be less than 2 over minus lambda, where minus lambda is the coefficient of y on the right hand side. And if you extend this to the non-linear case, then it is coming in terms of the eigenvalue of the Jacobian matrix J, where J is the Jacobian matrix of the right side function f with respect to y. So again, h should be small, and this example I am taking to show the numerical implementation. So before we go solve this problem, let us see how the solution look like. So this test problem or this initial value problem is considered by the previous speaker also, and I have taken purposefully this. So the exact solution is y of t and x e to power t minus t square. And initial condition at time t equal to 0, y is taking the value 1, and we are interested to find the solution in the entire interval from 0 to 3. Okay, so if you put in the Euler method here f t and yn, instead of that, if you are putting 1 minus 2 t n yn, so you are going to get this formula for the Euler method for this particular problem. And uh, we can see that we have kind of discretization things underlying going on here. Those like it's a very good question. Like people ask, what is the solution of a ODE? So we say it is a curve. We always say it is a continuous curve in this particular case. So it's a continuous curve. But in computers, nothing is continuous. Everything is discrete. So when I am saying what is the solution of ODE when it comes for the computer or in MATLAB, then the answer should be it's a vector. It's a vector which stores the values of solution at different given points, given points. So if I see the solution of the underlying problem, then which is shown here by the red color line with the red color circle, then actually each circle or each marker represents the instances of t. T can be anything. It can be time. It can be some point in the space. So it is the each circular point or each circle denotes the one instance of the variable t, and it is storing. So if I count all these, so the solution of my underlying problem will be having these many elements in the vector. So we need to actually work in the discrete sense, basically in the sense of vectors and matrices. Nothing is there as a continuous thing. So in order to solve this problem, actually the implementation is very easy for this problem. So you know what is y0, which is given in the original equation. You know what is t0, and you know what is capital T, the final time t3. And you know that we have increment the time or the space, the variable discrete value of this variable t by h at each time. So it's a incremental value. So if we want to implement it, we can do it in MATLAB in this way. So I have written this in the slide also, but let us go and see if we want to do it in the MATLAB. So let us see. Uh, uh, just let me know if these fonts are clear to you on your screen. So what are the things? So I will type here something which I want to mention. So what we know, this is the question. So we know T naught. T naught is 0. We know capital T or T final also you can write. Capital T is 3. Then what we know? We know the initial value of y0, which is equal to 1. All these things are given. These are things which are given to us. And what we want? We want to discretize the interval. We want to discretize the interval 0 to capital T, or I write T0 to T into discrete in small in n parts with each interval uh, with the uh, with the step h. So let us define h is equal to 0.1. I can do, there are very ways you can do this, and I am taking my, I am discretizing the time, and I will use t because it is all the time it's coming t. So t is generally we use for time, so I'm using time t. So I want to discretize the time interval, and I am storing this discretized value in a vector, which I denote as a variable uh, t. So yesterday we discussed that how we can actually use the colon symbol. So it was like start value, then increment, and then end value. So if I run this code, what I'll get in t, we are getting these many, around 31 values. If I take the h equal to 2, I think that will be much better. And if I run the code, I will get total 16 values in t. So basically, my interval from 0 to 3 is discretized, and discretized with these grid points, or these discrete points are the value at these discrete points are stored in the vector t. So what uh, so at time t equal to 0, we know what is the solution, and we want to find out what is the what is the solution at time t equal to 3. So in order to do, if we want to use the Euler method, so Euler method gives us the way that if this solution is known to us, how can we compute this solution? Once this is known to us, we can go and compute the solution at this index and at later stage. So one step we are going, one step we are going. So basically, I have to define my solution vector. So I have to define. I have to define my solution vector to store the value, discrete values of discrete values of solution discrete values of y. I have to define my solution vector y to store the, okay, so I have to put here y to store the discrete values. So in order to do that, I will define my solution y, and yesterday I talked about zeros function, so I can use this, and then I can talk about what is the size of this y. What should be the size of the y? So the size of the y should be same as the length of t. Okay, and I can define a variable n which is storing the length of t for the later state. So now we have a zero vector with the variable name y, and I want to store the values of the solution into this. But we know the what is the first entry of this vector. First entry is nothing but the solution at t equal to 0. That means y0. So I'll put it equal to y0. Now y0, it okay. It is. I can put y0 or I can put 1 also, but I am putting y0 here. Now y1 is known to me. I want to find out what is y2. Y at index 2. And if I look at my expression, the expression is like this. So y2 is equal to y1 plus h times 1 minus 2 at t1 into y1. So this is the way I will read it. So I can write it here. Y2 is equal to y at index 1 minus or plus, basically it should be plus now, plus h times star 1 minus 2 star, star is for the multiplication, t1, and then you have star y1. So this is the first step. So I got y2. I can then go for y3 also, and I can write this whole whole statement with the index 2. And if I keep on doing, I can find out y1, y at 1, y at 2, y at 3, and y at capital T, or y at 31 or 16 in this case. But this is the way, this is very crude way of doing the things. What we can do, we can use the loop facility of MATLAB. So instead of writing this way, I will use the loop. So in order to do that, let me start the loop. So for I will take my index vector or index variable I. It is equal to 1 to n. N is the length of the interval or length of the vector t. And then I am writing here y at 2. So I will write here I equal to, so y1 is already known, so we will get 2. So from 2 to n. So y I is equal to y I minus 1 plus h1 minus 2 star t I minus 1. I hope so I'm not doing anything wrong. Then I minus 1, and then I can write and if I run the code, it will give me all the outputs on the screen. What is happening? So this is the solution which we computed. I can actually now plot my t with the solution vector. So we can plot it and let us see how it comes. So it is coming very poor, very poor, and we are not happy. First, we want to suppress this calculation of y all the time because it is coming here. So yesterday I told you, in fact I mentioned how we can suppress the output. So we can suppress by putting a semicolon. Now if I am running it, let me first clear my command window. So if I run it, I'll get this, but nothing comes on the command window, no output. Now let us change the step size h equal to 0.1 and let us see how it is coming. Again it is coming this way, so I think 1 plus 1 minus, it is 1 minus 1 y plus, okay, y minus 1 plus, oh okay, I have to this is correct only. I think some mistake is happening. 1 minus 2n. Okay, let me check the code here. 1 minus 2n. H is not multiplied here. H star. Now we can run the code and it is coming now. So I missed the H. So this is the way we can actually write the code for the Euler method. In fact, you can write the code for the exact solution also. Exact solution can be computed by the formula given here in this y equal to t to power t minus t square. So we can actually write here uh, y exact. Okay, we can write directly using the vectorized functionality. So I can calculate here ye is equal to MATLAB exponential t minus t vectorized calculation. So I think once it is done, we can actually call the figure command. It will give me a box for the figure. I can assign the number of number on the box, and I am putting my numerical solution with this kind of marking scheme, circular and with line, and then I will put the command hold down so that I can rewrite my exact solution. And if I run this, I will get my solution. So this uh, dotted line, or the dotted line, is the approximate solution which we got from the Euler method, and this red color line is our exact solution. In fact, you can put the mm, uh, this some of the annotation also which is required. So for example, if you write so I am using this plot p y x, and I'm in this slide we have using b means b blue color and line width 2, and we can actually put the legend exact solution and order approximation. So depending on the order, so in this code on the slide, first we plotted the exact solution, and in the second line we are plotting the solution of given by the Euler method. But the code which I wrote, it is slightly different. I have written, I plotted first the computed solution y, and the, so I can write here legend, and I can here put y and ye, just for our understanding. So if I now again draw it, I will get this. So I can get here the legend also. So this is the way we can actually make a simple code for Euler method to solve this problem. Uh, in fact, if I go and put h equal to 0.5, let us see what happens. So it is still working. If I, yeah, this is okay, but uh, let us see one example. So this is the problem which I considered, and this is the solution by the Euler method. And this code I have implemented, but slightly differently, because here it is in the slide. It is much more, aesthetically better to make the plot aesthetically more beautiful. We are doing it. Yeah, for the benefit of the audience who do not know the MATLAB plotting. Yesterday I mentioned this, but this figure command will open this window for you, and then you can use the plot command. You can assign the color of the line and line type dotted with the, this is circular line, circular marker. You can use square marker also. Then you can mention the line width, and you can put the label of the figure on x-axis and y-axis. And if you put title, then you will get comparison of exact and Euler method solution and legend, and then grid on is the functionality which provides you the grid, which we can see from the in the figure. So this is the code we have already implemented, and this slides actually talk about uh, what happen if h and lambda are not good, like if they don't satisfy the stability condition. So this main body of the function is same, but here we are using two loops. One loop is actually only this slide is having only one loop. So we have taken a very small or very large negative value of lambda 10 minus 15, and we are taking different h values 0 0.01, 0 0.05 and 0 0.1, and we want to compute the solution at t equal to 1, and we can define the uh, type of marker also. It's a basically kind of a dictionary or MATLAB set. It's basically a set, so you can define the markers and the color, and then you can actually run the code. So the point which I wanted to mention here, so here is the main body. You are just using the for loop. Yk plus 1 means the next value of the solution is computed in terms of the known value of the solution. And if we go and see the plot of this code, what we see is this. So when the lambda value is minus 5, different value of h are taken, and we can see that all the red color, that the black one is the agent solution, but all the red color one solution are uh, behaving nicely, like it is quite good, the state line when h is 0 0.01, but when you are taking h is equal to 0 0.1, bigger than 10 times bigger than the previous value, then it is drifting away from the z solution. But if you take lambda value equal to minus 50, then h equal to 0 0.1 is actually making the whole thing unstable. So such kind of first order ODE are called stiff system, and basically when you have a stiff system, you Euler method put a lot of restriction. So this I have mentioned here for stiff problem. When the Jacobian matrix has large negative eigenvalues, then Euler method requires a very small h, and that therefore it becomes computationally costly. And it is a very primitive method, Euler method, very primitive method. Now a lot of methods are there which are improved, and probably some of the speakers will talk about them or already have might have talked about them. But my job is to just do the coding. And this is a modified Euler method. If the time will permit, I will try to do the coding for this also. I have not included the coding part of this. So with this, I think I have come to yes, I think I have to go a little faster. But we started like some 10 to 20 minutes late, so we can. I think I have still some more time. So the second problem which I am talking is the PD. Again, we are considering first order PD, and it is a very popular PD. Most of the time, this PD actually people use to devise any numerical method, and then it is that numerical method is used to get tested for the complex problem. What kind of complex problem? So that the problems which comes from the traffic flow, it can be from the astronomy, it can be from the fluid dynamics. So those equations are called equations of conservation laws, and this is the simplest equation which falls into that category. So it is actually essentially models wave propagation, and it shows how a quantity transport or advect in absence of any diffusion. There is no diffusion, so how it will advect. And if you want to find out the solution of this equation, this is again like my initial condition is given where f can be a smooth function or it can be a discontinuous function. So initial condition can be smooth as well as discontinuous initial condition. So how we can find out the solution? So basically, when I want to say that this this problem, uh, the solution of this problem actually propagates um, in one direction without changing its shape. It preserves shape. The preserves its shape means the initial condition, whatever is the solution at time t equal to 0, that will be preserved and it will propagate either to right or left depending on the characteristic or wave speed a. Let me show you this here. So this is the problem which I have taken. I will be talking about. So this is initial condition for the linear advection equation or transport equation, and uh, in the MATLAB window you are seeing one of the frame. So basically, if you take it from minus infinity to plus infinity, it is actually propagating from one frame to another frame, and we have taken here kind of boundary condition which is called periodic boundary condition. I will show you the implementation of that also. So I think this makes us clear like how the solution is propagating. In fact, we have taken here a equal to 1 in this simulation, but if we want to take, if we take a equal to minus 1, then you will see the solution will start propagating towards left. Okay, so this is actually a pure transport equation, which we are going to discuss about the numerical. So uh, it is like if we take the total derivative of u, and if we consider dx by dt equal to a in this, in order to find the solution of this equation. So if we take the total derivative of u, we will get the equation number 3. And if you put dx by dt equal to a, then your total derivative expression is equal to nothing but the original equation 1. So it has to be equal to 0. So what it shows, that if you are taking dx by dt equal to a, then your solution will remain constant. Or you can say it a little bit more aesthetically, that the solution remain unchanged along characteristic equation, that is dx by dt equal to a, or the characteristic line x minus at equal to constant if you integrate it. So what is the characteristic line? So here you are having the solution emanating here you have x-axis, so you have x0 here, and if you look into this, so the solution will remain constant along this. So like the solution at the point u 1 comma 0.5 will be same as the solution along this characteristic at time t equal to 0, and that means the start of the characteristic curve or line. So this is the uh, property of this equation. So that means you can actually represent this solution in terms of the initial solution. And what is the initial solution? Initial solution is your f. It is given here, f of x. So you can actually write u of xt equal to f of x minus at, where x minus at is this characteristic. So that's, so basically this represents that solution, whatever initial condition is there and initial solution is there, the same solution will propagate either to the left or to the right. And this problem can be solved by various numerical method, and I am again talking the first order method. And here I have given the example that the solution, if the initial condition is this, then the final solution at time t will be exponential to power minus x minus at. So instead of x, you are going to substitute x minus at, and you will get the solution. It is the exact solution. But what about the numerical solution? So you can actually uh, go and try different methods for solving this problem. There are very good methods available, but it's actually a very complex problem also when it comes to the numerical computation. I will not go into the detail. So what we are doing the du by dt or del u by dt. The partial derivative of u with respect to true is discretized by the forward difference formula, and the space derivative del u by del x is discretized by this backward difference formula. It is also called upwind difference, but let us assume that this is let us take the backward difference formula. So in time we are using the forward difference, and in space we are doing the backward difference. Forward because we are taking n plus 1 minus n, the quantity at n plus 1 at time label minus the quantity on the same grid point I at nth time level. And when we are coming for space, what we are doing, we are freezing the time. So at nth time level, the difference of the quantity at grid point I and I minus 1. And we are, if we take this and put into this equation, equation number 1, ut by forward difference and ux by backward difference, you will get this scheme. This is your update formula. So initial condition at n equal to 0 is known. So ui at each I is known when n is equal to 0. So you can go for u1, u2, un. And when this numerical method or upwind method is stable, so there is a condition called CFL condition. It is a relationship between delta t and delta x. So like you can choose delta x and then that will define your delta t, or you can basically this is the idea, like if a is constant, you can choose both of them a priori for solving like for the stability, but sometimes a is dynamic and it evolves, so that time you have to find out delta t, because delta t is the only controllable parameter here. Once you choose delta x, and when a is free, then only delta t is there, which you can use to satisfy this CFL condition in order to ensure the stability. And this quantity a delta t by delta x is called Courant number. This is the theoretical background. Let us see how we can solve this problem in MATLAB. So again, I am taking two different cases. In first case, we have taken very nice smooth initial condition fx equal to sin pi x, and case 2 here ux0, that means fx is equal to mod of x if x is less than mod of x is less than 1 by 3. So basically it is this initial condition, which we have taken, and we need to do the programming for this problem. So let me try. I have the code here written. This code is already there, which I have implemented, but I want to try to write the code for brevity. There may be some mistakes which can be there, but I hope you will understand the complexity of writing the live code. So I'll write here live. I'm upwind dot n, and I will take one of the condition. Okay, so let us define how many grid points we want in space. So we'll define n of x. Okay, so define the grid parameters. So I will take variable nx and I will define nx equal to 100. Then I can define my length. So length is here from -1 to 1. So my length is 2. So I'm defining L equal to 1 um, because domain length is 2, and I will define my dx. Dx is nothing but the delta x. So dx is your grid spacing. So I can define it 2 into L divided by nx. So this is your grid spacing. And after that, yesterday I talked about linear space function. So I want to store the entire domain into discrete vector x, and how many parts I linear space, and then I can write here minus L to L and then nx. So what it does, it creates vector x storing the domain uh, with the nx grid values. I'm just writing it. I hope it's visible. Is it visible to all of you? And then I can
Yes, yes,
define.
it is visible, sir.
Okay. So I'm doing this. I'm trying this. So, and I will take a equal to 1 because the condition here is a equal to 1. And then we can take the CFL condition 0.8. So CFL is equal to 0.8. And I can then define dt equal to 0. Okay, CFL star dx. If you take delta t, so it's equal to CFL times delta x. So this is the way we can control the stability condition here. Then so we got delta t. I will write it here time step. Then what else? What else? T equal to, I think. Okay, so we have taken here. We are taking a periodic boundary condition. So what we assume that our solution or the initial condition is periodic in nature. So from -1 to 1, it has a square shape or sine wave. Again, if you go from, for example, sine pi x, from -1 to 1, it is having same structure as it will be having from 1 to 3, or from -3 to -1. Like the period is 2. So every period, the same function is repeating in the entire infinite or on the real line. So we are taking periodic boundary condition because it's easy to implement, and not much is there to bother about it. So we will take the period t equal to 2. So we have the initial condition, and we want to take the final time t equal to 2. Any multiple of the period we can take, and I can put it here as t underscore final for better understanding. And then I put number of interval in t direction. So it will be, I can use rule function divided by dt. So now we know how many time steps are there. Number of time steps. Then what else is required? Okay, so I'll choose only one initial condition. So let me choose the initial condition. Initial condition. Uh, initial condition. So I can store that initial condition in U0. So U0 I'm defining as sine times pi is inbuilt variable in MATLAB, and I can multiply. So if I want to see how is this looking at the moment, so if I run this code, uh, okay, I think I have a mistake here. Okay, so this is the initial condition which we have taken, or you can say this is the initial solution also of our problem. So now this is okay. We are good to go. So initial condition is stored in the vector u0, and I can initialize the solution. Solution we are taking. So u0 is our u at time t equal to 0, and we need to create some vector which can store the value at the next time level. So first we will keep this intact and leave it, and we will define a new variable u, and here I am going to use u0, and u underscore exact will be storing the exact solution. So basically we have to define the vector u and u exact at the same size as u0. So there are many ways. So you can define the zeros as 1 comma t x is a row vector and u0 is a row vector. I'll take 1 2 variant of x. So I have defined these two vectors. So like initializing the vector to store the exact solution, and here we are initializing the solution. Okay, so now I think we are done. I think we are good to go. So what I have done, I have stored first the initial condition or initial function u0, and what I'm going to do, I'm going to use, so I am going to use u vector u to compute the next vector, uh, compute the solution at later time in another vector u exact. Okay, so this is what I'm going to do. Oh, u next, sorry, u next. Exact already is there, so u next. Okay, so now we have everything. We will start using loop. We are going to use loop, so I'll use for loop. So basically we have the solution. It's not here. Okay, so we have the solution given at suppose this time level, and we want for this time level on this. Suppose we have the solution at a given this time level, and we want to calculate the solution at time at the later state. I have not given figure for that. So for I equal to 1 to nx, or I will start from 2 because 1 is 1 will create the problem, so that 1 has to be taken care differently. So u next I is equal to u at I minus a star CFL number, basically. So dt by dx star so here you have a dt by dx and this. So ui at next time is equal to ui at another time minus a delta t by delta x, a delta by delta x, ui at another time level minus ui minus 1 at another time level. Sorry. So another time level we are denoting by ui and ui minus 1, and we can put and. So what we did, we have computed u next from index 2 to nx except the u1. So in order to calculate the u1, we are going to use the apply the boundary condition. Apply the periodic boundary condition at to compute u underscore next 1. Okay, at index 1. So this can be done as u next at 1 is equal to u at 1 minus a star dt by dx star, and here I am going to put uy minus u and minus 1. Okay, so here I have used some property of MATLAB vectors. So let me explain that to you. So u0 is given. Okay, I'll take a smaller value 10, and then if we run this code, clear all is a command so that everything will go from the workspace. And now let us see what is u0. So u0 is a 10 length vector. It is a 10 length vector because it is taking the sign value, sin pi x, from -1 to 1. So you can see that this value is same as this value with the sign change, and this value is same as this value with the sign change. Now let us look at, if I put u03, what value will get? We'll get this value, u0 at index 1, u0 at index 2, index 3. But if I put u0, and what will happen? I'm getting this value. It is showing 10 to the power minus 16 approximately. So it is coming here, this value. But if I put, so basically for any vector, when we are indexing with and keyword, it points to the last element of the vector or the array. So as we can see, since we are using periodic boundary condition, so so suppose you have the boundary here, so the value after this will be same as this value, periodic boundary condition. If you look at sin pi x, x equal to -1 to 0.1 comma 1, y equal to sin pi star x, then if you plot x comma y, you will get this. So if you can, so basically has to be this way. So you are getting the discrete values like this. And when I'm saying periodic boundary condition, so if I want to find some value here, if my formula requires some value corresponding to this point, so that point will be same as the value at this point because of the periodicity. It is same. This value is same as this value. This value will be same as this value. Similarly, the value which will come on the outside the right boundary will be same as this value. So it will be like this. So what I am doing, I am putting and minus 1, so that instead of uh, so basically you can see that the value, let me put, if you see u0, so u0 is, so this value and this value is same, as I said, minus 0 and 0, so almost same, it's coming almost same because of the periodicity. So what I'm doing here, for going, because if I put I minus 1, it will be u0, but MATLAB does not allow index 0. MATLAB start indexing from 1. So basically, if I want to write here u0, it will throw my error. So you can have the value from 1. So when I'm running from if I'm running from for 1, if I put here u1 minus 1, I will get 0. So instead of that, I am just using the value from the right boundary, and first value just before the boundary. It is difficult to tell here, but yeah, this is it. And if I want to, and then I have to put here time t equal to t plus dt, because first I will calculate and again I will keep on updating. So t equal to uh, t plus 1. Okay, so we have taken solution in u, initial solution, and we computed the u at next, and once we computed all the value of u, we can increase t equal to t plus delta t, and we will again swipe the value of u next into the old u, and we will keep on doing this. So I can put and here. So it's equal to t plus 1. Okay. And this is correct only, and I will put here, because what up to what time we have to go, so I'll put here while t is less than t underscore final, and I'll put here and. I think this should be okay, and then I can plot x with the u next. Let me check if it is working fine. What is t? T is not defined. So we have to define t also, because t is the initial point, t equal to 0, and when we define, so now I think we can run this code. Now this is the solution which we got. So we will define our mesh. So now we have this. This is a computed solution, and I can put here some. Since we are taking at the time t equal to t, period to t equal to t is equal to 2, we can actually consider the initial solution as our reference solution, or you can use the U0, and this is your exact solution. It will be, it's not exact, but it's initial condition, but it will be, it can be treated as an exact solution. So you can see that for the blue dotted or circular line shows you the approximation which you received by Euler method, and the red one is the exact solution. You can actually calculate the exact solution also. So that can be done as u underscore exact, which I have already defined here 0. So I can put here u of exact equal to, here I am going to use circular shift function of MATLAB. Circular shift does nothing but it circulates shift the initial condition, because I said the initial condition is having uh, the same. Basically, in this case, what we are seeing, the initial solution propagates with time without losing its shape. So that is the thing which we are using in order to compute the solution. So instead of using this writing another separate code, we are using this circular shift, and I am using the facility of MATLAB to compute this. This is the shift at each time level, and I can put here plot. I can write here. I can write here exact. No, this is not exact. I will not write here. Okay, here you have x. If I run this, let me see what. T minus I. So here we are getting the solution slightly different. I think some mistake is there. I need to work on it. U0. How many? Can write here the exact solution. I want at time t. I put here 2. Let's see. Or not. Now we got the solution. Exact solution also is there. Exact solution can be written as this. I will remove the initial condition, and I will put the solution at time t equal to 2. So this is the solution which we are getting. The black one is the exact solution, and the dotted one is the solution obtained by the Euler method, or sorry, FTBS method, forward in time and backward in space. I can put here then instead of this I can put here t. So now I can change my time also. Instead of taking 2, I can take my t final equal to 1, and I should get the solution. It's not coming in the way I thought. Why? Okay, I'll put here t underscore final, and then if we run, I don't know what happened. Something I'm missing here. Outside this. Okay. Missing 1, 2, and on the maybe this getting wrong. Okay, there's one shift is there which I'm not able to find out why this is not happening. But if I put here T, it's not changing. I think I have to good look back, but okay. So for time being, we will just use uh, solution with period 2. But in the original code, in the slide, the code is I run that code and it was perfectly fine. You can see here we are getting one error or a highlighted thing like a warning. So that is happening because we have not assigned the enough required memory for the vector u next. So we can actually define, and it is saying that you are not using it. So this is also creating problem. So I will here put u suppress this mistake, this error. We can put here u next equal to 0. So now you can see that this error gone. And since we are not using u exact in the plotting, it is showing highlighting this that this is not being used. If you put cursor here, might be unused. So because we are not plotting the exact solution, it is showing. If I put r, oh sorry, uncommented, it will go. So it is. Oh, we are using here. It should not be used here. Yes. Mm. Anyway, I think exact solution we will remove for time being, and for t equal to 2 we are calculating, and we can see our code is working fine for all the things except the circular shift function is not working the way I thought it will work. It was working. I don't know what happened now. So this is the way we can write the code. You can actually change the initial condition also. So this is the first initial condition. We can change the initial condition. The next initial condition is I equal to 1 2 nx, and if xi is absolute value of xi, absolute is the inbuilt function, is less than 1 by 3, then you are taking u0 I is equal to 1, else u0 I equal to 0, and then you can put and. So I said that each if should be completed by and. Similarly, every loop should be ended by one and here I am commenting it. So if I run this code, I will get this solution. So this is the initial condition which I am using as a reference exact solution because I am taking period 2 and a time t equal to multiple of period of this periodic function, and this is the computed solution. So there are a lot of things in this plot which we can discuss, like the approximation is not very good because this is the red color is the right solution, correct solution, and we are going very very smooth approximation for that. So that is happening because of the low accuracy of the scheme. This is first order accurate in space and time. You can increase the number of point here to 1000 and you will get somewhat better approximation, but at the same time computationally more costly. So with this, I think in this slide the code is there. You can copy paste if you are using, but same code can be written in Python and C also. And with this, I think I am done for today. And Professor Rajiv, are you there? Hello.
Yes, sir. Yes, Professor Ritesh.
Yeah.
Thank you, Professor Ritesh, for a very nice and very wonderful lecture. And I'm sure that our participants will obviously be benefited by your lectures about the solutions of numerical methods using the MATLAB. And you have today shown on the MATLAB platform how to run the code. You have written many codes also. So, participants, if you have any question, you may write in the chat window. I'll wait for another 2 minutes. If you have any question, please write in the chat window.
I think there is no question. It's quite late today.
Yes, it seems no question. So let us again thank to our speaker, Professor Ritesh Kumar Dubeji. And Professor Ritesh sir, may I request you to kindly share your slides also in terms of a PDF file so that we can upload it on the Canvas platform so that our participants later on, if they want, they can use it. Uh,
Yeah, actually, yesterday's slides I already sent to you.
That I have already shared on the Canvas. Today the slides also you can
I'll
share
share.
with us.
I'll share
Yeah,
it
yeah.
right away.
So
I'll
so
share it.
so I will upload on the Canvas. And thank you very much on behalf of EICT Academy, on the behalf of organizers of this FDP, and on my personal behalf. I express my gratitude to you for delivering this very wonderful lecture for our participants of this FDP. Some participants are writing live coding was very useful to learning. Yeah, so participants have enjoyed your lecture. Satyendra Prasad, thank you. Thank you for your feedback. Thank you, Dr. Atul, for your feedback. Amit Saraswat is saying, sir, I am unable to get the video link. Amit, when you will go to the Canvas, in the module session, there is a tab of module. If you click on that, then one new window will come. On the top of that window, there is a link for the YouTube recording. Just you click on that, then the recorded lectures will be opened in another browser window, and the YouTube channel will start streaming the lecture. Okay. So still, if you feel
Yeah.
any problem, you can write on the WhatsApp, and my students, my assistant, they will help you to get it.
Okay.
Thank you, thank
Yeah.
you, thank. Yes,
Yeah.
yes.
I sent you the slide. I sent you the slides now. I
Okay,
emailed
okay.
you.
Yeah. So thank you, Professor Ritesh. Good day. Bye bye.
Bye bye.
Yeah. So participants, I can close this session now. We will again meet tomorrow at 10 a.m. Thank you. Bye bye. Good day.